We're back. Thank you to the artists. Beautiful. So let's go and take a look again at the function, password checker. And now, first of all, does this function check the password correctly? Does it do its job as a password checker? Let's assume I have no implementation at all. I'm just running this in theory. Does this code do its job as a password checker? So I see I have some people who aren't very satisfied. So can somebody explain to me why this is a bad password checker? And let's assume I don't have a timing attack. Oh, so it's brute force. Okay. Shimon, I don't think I can test for length because I have a perfect implementation with no timing satchel. Okay. I cannot a guest user. Who is the guest user? Please identify yourself, guest user. Alex. Hi, Alex. I cannot guess the length easily without a side channel because I will send something and I will get immediately. Let's assume I have a perfect implementation which does not have any timing leaks. I am unable to measure the timing for some reason. In such an implementation, I cannot measure the length. So if I'm running in a perfect world, this is a perfect implementation. It checks the password. It's protected against buffer overflows, and it does a great job. It does a fantastic job, one of the best jobs. But now let's try to attack it, the implementation. And so let's go with Shimon's suggestion. Now let's assume that the function actually each line of code it executes takes some time. So how do I use this? How do I attack this implementation using timing attacks? Okay, first I try to get the length. So OL, how do I do this? What is my data structure? Let's assume that the length is between 1 and 16. Okay. I try different things. Let's assume that the length is between 1 and 16. What is the data structure I need as an attacker? I have an array of size 16. Okay. And how do I fill in the array? I check the time it takes. So what do? I run this function. And what is the input for the first time I run it? 1. Okay. 1, 1. Okay, I run it for 1. I get the answer. The answer is no. This is not the right. Password. But indeed, I'm not looking at this. I'm looking at the side channel. So I save in my array the time. So now I have an array of size 16 with 16 times 1 for each length. So what do I do now? Okay, so I look at the longest. So you're saying the largest value in this array corresponds to the correct length because why? Because if the length was incorrect, the function would exit in line 5, right? But if the length is correct, then it would exit in line 10, right? It will exit in line 10. So instead of line 5, it would exit in line 10. So I have an array of size 16, and I take the largest value. Yeah, if I get to line 14, if I guessed the right password. Okay, but tell me something. What if I'm not really certain about my measurements? Maybe they're, I'm measuring over the internet, or I don't have a very accurate clock. Um, what if I want to measure? I want to be more confident about my measurements. What do I do? Okay, so I need to do more measurements. Okay, so now my data structure is going to be, instead of a vector, it's going to be a matrix. So the matrix is 16. This is the possible length between 1 and 16 characters. And what is the width? It's the amount of measurements I want to run. So maybe 100 times. So I run it 100 times for length 1, and I have now a first row in my matrix. 100 times for length 2. So after I run it 100 and I run it 1600 times, and I have a matrix of size 100 times 16, which is full of different values. Now what do I do? Okay, I take the average of the rows. Okay, so how do I know which row to take? Okay, I look for the row with the highest average, right? Okay, so I'm going to talk a little later in the course about statistics, but I want you to think a little about what we did right now, and what was the signal processing behind what you did. What you're trying to do, you were trying to get the signal out of the noise by averaging, and yeah, we'll develop a little more next week, God willing. But again, after a constant amount of time, I will know what is the right length. Let's say the length is 5. What do I do next? Okay, right. So this is Alex again. Alex, okay. So I am trying, instead of 1, 1, 1, I'm going to try 2, 1, 1, 3, 1, 1, 4, 1, 1. And then what happens? How do I know I got to the right one? I don't get through so fast, right? So the timing is going to be different. So again, if I'm choosing the wrong character, then line number 9 is going to run once. If I get the right character, then line number 9 is going to be running 2 times. And then it's going to go to line 10, right? Actually, it's line number 8 and line number 9 is going to be run. So the timing is going to be longer. And again, the right way to do this is going to be a matrix, right? And I'm going to take the average. By the way, don't get addicted to the average, and this is a little hint for you. So I will be able to get the next character, and then I will get the next character, the next character. If the password is 11111, then I'm a very happy hacker. Then by the way, Alina, you want me to open this? The right way to do a brute force attack is not to try all the random numbers, but actually to try the likeliest numbers first. 111, 1234, 3580, 15357, and so on. Dictionary attack is the right phrase to use. It's better to use the likeliest letters first. Does anybody here want me to repeat the timing attack on this password checker? Okay, so I will repeat it very briefly. What I'm going to do is, first of all, I'm going to, I need to stop the poll. First of all, I'm going to make the function exit at line 10 instead of at line 5. So if the length is incorrect, it will exit at line 5. If the length is correct, it's going to exit at line 10. So I'm going to try increasing lengths and all sorts of different lengths. And one of the lengths is going to be the correct length. and then the function will exit at line 10 instead of line 5, and it's going to take a little longer to run because of that. And once I know the correct length, the next thing I'm going to do is, do I assume that we make an infinite number of time? Yes, this is in my attacker model. I can assume I can make an unlimited number of cookies. Infinite is kind of risky, but unlimited, right? It still takes me time. It still might be impractical or nonsensical if I'm trying to get into, I don't know, I'm trying to get the elevator to go to my floor very quickly. I don't want to spend an hour doing it, right? So if I do it, if I get to line 10, it will take me longer. And then I'm trying to get the function to run line 8 and 9 as many times as possible. So if I get the first character right and the second character wrong, it will run 8, 9, 8, 9, 10. If I get the third character right, it will get the second character right, will be 8, 9, 8, 9, 8, 9, 10. It will be running longer and longer and longer, and in the end, I will get the password. So, is this a good attack? Let's see. Let's analyze if it's a good attack. And the question I should be asking is, how long did it take me to get the key out without the attack? And how long does it take me with the attack? So let's do the measuring. So let's assume that getting the length of the password is actually constant time. I don't really care about it. Let's assume that the password is always 16 characters. Okay, so 16 characters. I'm going to put this here. Hopefully it will work. Do you see the shared notes? You see them? I don't know because I can only chat or so 16 characters, and I'm going to assume there are 26 letters. So do you see the shared chat? Okay. Shared notes. Shared notes. So how much do I need to do the brute force? I will have to try all 26 combinations for the first character, and the second, and the third, until the 16th, and I will need to get them all correct at the same time. So I will need to do, indeed, 26 to the power of 16. And what is this number? I don't know powers of 26. I'm going to do, I want to find what is the power of 2, which gives me this, because I know that 64-bit security is pretty good. I know 64 bits is secure. 20 bits is not so good. 100 bits is really, really nice. So I want to find out how many bits this is. And I'm going to use a very simple quality which we learned in school, which is this, right? So I can take out the 16 from the log, and I can actually use any kind of basis for my log. If I don't have log2 on my computer, I can do this. So this is my final derivation, and this is about this is where is my this is about 75. Something around 2 to the power. It's somewhere around 2 to the power of 75. Okay, so somewhere around 2 to the power of 75 to brute force a 16-bit alphanumeric, and not alpha, lowercase alpha character. 2 to the power of 75 is good. It's secure. So we assume that the nation-state attacker can do 2 to the power of 64. So 2 to the power of 75 is pretty good. This is before the attack. Now, again, I'm assuming I don't have a dictionary attack. Let's assume I have maybe an algorithm that generates completely random passwords and gives them to the user. So this is before the attack. Now, after the attack, how do I get the key out after the attack? So to get the key out after the attack, I needed to find the first character. And then I needed to find the second character but I didn't have to get them right at the same time. First, I had to get the first character, and it took me 26 times constant times something because I had to do maybe 100 repetitions. And then the second one, it took me again 26 times something. And in total, I had 26 times 16. Indeed, I have 26 times 16. And log 2 of this is a little more than 8. So this is going to be a little more than 2 to the 8 and a little less than 2 to the 9. So this is a good break. So this is an effective attack. But I have to repeat it 100 times or 1,000 times or something like that. Still doesn't matter. As long as the factor isn't ridiculous, you don't have to do 2 to the 40 repetitions, you're still getting a nice security advantage. Now, indeed, I'm using O notation, big O notation, and I think everybody here is familiar with big O notation. Who here wants me to say a little about big O notation? Should I say something about big O notation? Well, okay, I'll say something about big O notation. Big O notation means that O of something, for example, O of n, means that n is the length of the input. You can multiply it by whatever constant you want and add whatever constant you want, and this is the value you get. So these are called complexity classes sometimes. So O of n is linear time. And 2 to the power of n is exponential time, and exponential time really blows away really quickly. And I will give you a very nice motivating example about the difference between linear time and exponential time. Let's say we have a system which is already deployed, already shipping, and the security engineer, the systems engineer comes to me and tells me, listen, I found that there is an attack which is being developed in the university of whatever, and they've nearly broken our system. I want you to make our system twice as secure as it was before so we can stay protected. So if I had a linear time system, a linear time password checker, and I wanted to make it twice as secure, what would I have to do with the length of the password? By how much would I have to increase it? If it's a linear time system. I can't. It's already shipping. All I can do is change the length of the password. And I want to make it twice as secure. Right? I need to make the password twice as long, indeed. No, if I can't add one character. I have to make the path character twice as long. Because if I'm talking about a linear time attack, to make the system twice as secure, I have to make the password twice as long. And which makes the execution twice as long, and the storage twice as long, and everything is twice as terrible. Now, if it's an exponential system, and the system engineer tells me make it twice as secure, what do I have to do? Shimon, you can just copy paste, add 1 bit. Indeed, I just add 1 bit, and if I add 1 bit, the system is twice as secure because the attacker needs to get all the bits correct at the same time. So exponential security is much better. Now, so make the system, raise it to the power of 2. You're talking about if I found a logarithmic attack, and I don't really want to think about that. That's a disaster. To get a logarithmic attack, you would need the system not to look at all the bits of the input, because even just looking at the bits of the input is linear time. So yeah, let's not get there. So this is the attack, and now I want to protect against it. So I prepared a couple of defenses in slides in the presentation, but let's just hear some suggestions from you. How can I make this password checker more secure? Any ideas? Okay, so okay. So everybody get out what you're typing, and then I'll discuss it all together. Okay. Can you suggest any changes to this function to make my password checker secure against timing attacks? Any tricks? Okay. Hash padding. Let's okay. If you have something in your text box, just finish typing, and then I'll read everything and react to it. Okay, fine. We're finished. Everything is out. Everything is come out. So let's see what we have here. What have suggestions? Okay. So Tamir and also El and also Roi are suggesting to use a hash. So I'll talk about hashes a little later. Hash is a really nice idea. I want to talk about it a little later. Let's talk about things which other things. So Lishai is suggesting to return only at the end of computation. So instead, in line 5, maybe I will say result is equal to false. And in line 10, I will say result is equal to false. And then I will have return result. Okay. Oh, yeah, I think you're suggesting the same thing. Checking the entire password and returning at the end. So going over all the characters of the password. And let's see. So I have a user purple guest. Who is the purple guest? Please identify yourself. Purple guest. Who? No. Alex. Who is the other one? Who is the one who did this logic correct and equals to end password equals? Yeah, Dima. Okay, fine. We should really fix this. So let's look at one of my implementations and see if I'm getting if I was able to